Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for evaluate division problem. Let's look at the problem description. We are given an array of variable pairs called equations and an array of real numbers called values, where each entry in the equations array, so equations of I is equal to ai comma bi, and value of I represents the value of the ai divided by bi. Each ai and bi is a string that represents a single variable. We are also given some queries where the queries of j contains seek variable pair seek j comma dj, and we have to find the value of cj divided by dj. We have to return the answers to all the queries. If a single answer cannot be determined, we have to return -1. Let's take a look at the example 1. The equations array has two pairs, a comma b, and the second one is b comma c, and the value for the a divided by b is 2 and the value for b divided by c is 3, and we are given queries with 5 variable pairs. Okay, basically we have to find a divided by c, b divided by a, and a divided by e, and a divided by a, and x divided by x. So the a divided by c's value is 6, because if we multiply this equation with this equation, the b's will be cancelled out and we get a divided by c. So we have to multiply the values of this equation and this equation. So 2 times 3, 6. And then we have b divided by a. Actually we are given already a value of for a divided by b. So to compute b divided by a, we have to return the reciprocal of this value, which is 1 divided by 2, that is 0.5. And then next equation is a divided by e. In this case, there is no equation that has the variable e, so the result for this is -1. And a divided by a is equal to 1. And x divided by x, the x is not present in these equations, so we have to return -1. Let's take a look at the approach to solve this problem. So we are given a list of equations and the corresponding values, and also a list of queries. Okay, so for each query we have to evaluate a divided by b, the first variable divided by the second variable, a divided by b, a divided by c, b divided by a divided by d, x divided by y. We can observe 3 cases in this input. Okay, for the case where the variables present in the query does not exist in any of the equations. Okay, for example, x divided by y, the list of equations do not have the variable x or y. So in this case, we cannot evaluate this equation, so we have to return -1. Basically these variables are not reachable. And in the second case, the query directly contains the equation which is already present in the list of equations in the input. For example, here a divided by b, already there is an equation. We can simply return the corresponding value present in the values array. So in this case, both the variables are present in the single equation. So it is straightforward. We can simply take the corresponding value and return it. In the third case, the variables are present in 2 different equations. For example, a divided by d. Here a is present in this equation, d is present in this equation. Okay, and also one more thing we can notice is a divided by d can be written as a divided by b times b divided by c times c divided by d. So b and b cancelled out and c cancelled out, we get a divided by d. So what we can get from this, in order to compute a value for an equation whose variables are present in different equations, we need to find the list of equations which can be multiplied, and eventually that will yield the value for the equation in the query. Okay, so in this case, to compute a divided by d, we multiply the value of equation a divided by b and the value of equation b divided by c and the value of equation c divided by d. So we get 2 times 3 times 4, 24. For this case, a divided by c, we have to multiply this and this. So the value is 2 times 3, 6. So this reminds us a graph. Like here, we have to traverse the graph and find all the edges which can lead from the starting vertex A to the end vertex D, right? And this is the case where the vertex is not reachable. The vertex is not part of the graph, right? We can model this problem as a graph problem wherein each variable in the equation is representing a vertex and each equation is representing an edge. Okay, specifically we can this is a bidirectional graph. Okay, because some queries have the variables in the reverse order, right? For example, here BA. So in this case we have to return the reciprocal of this value 0.5. Okay, so that's why we have two edges. One is forward direction and the other one is reverse direction. Basically this is a bidirectional. Okay, and each edge has its weight associated with it. Basically the A divided by B, the edge starting from A to B has a weight 2.0. In the reverse direction, the reciprocal of 2.0 is 0.5. Okay, so once we model this problem as a graph problem, all we have to do is, for a given query, traverse the graph starting from the first variable in that query. For example, A to C, we have to start from A and traverse this graph until we reach C. As we traverse each edge, we keep multiplying the weight and return it. For example, A divided by C, you start from A, you reach B because it is a neighbor. So the current value is 2. And from B, we can reach C. So the weight of that edge is 3.0. So 2 times 3.0, the value will be 6.0. So that is the output for this query. A divided by C is 6.0. So that's what I have written here. Basically we can model this problem as a graph problem, and each variable in the equation represents a vertex and each equation represents a bidirectional edge. And first we initialize the output list, and in each iteration we have to initialize the result variable to 1.0 and then perform the depth first traversal starting from the first variable in the current query. And as each vertex is visited, multiply the result variable with the value of the equation that contains the current vertex and its neighbor. The second variable in the query is reached, then we return the result. Okay, so we repeat this for all the queries in the queries list, and finally we return the result. Let's look at the flowchart. The input for this procedure is an equation array and values array and the queries array. First we initialize the adjacency list and the edge list map. The count is initialized with the number of entries in the equations array. Okay, so in this for loop we build the adjacency list as well as the edge list. The first element in the entry is start vertex and the second element in the entry is an end vertex. Okay, and first we check whether there is an entry in the adjacency list. If it is null, then we initialize with the empty list and then we append the end vertex as a neighbor of the start vertex. Because this is bidirectional, we have to do for the reverse also. So we check whether there is an entry for the end vertex. If it is not, we initialize with the empty list. Otherwise, we append the start vertex as a neighbor of the end vertex. Next, we build the edge list. Basically, this contains the edge and its weight. Okay, the weight is nothing but the value of that equation. Okay, so the forward direction is start plus dash plus end. The reverse direction end vertex plus dash plus start vertex. Okay, so we have to add an entry for the forward edge and the reverse edge. So we are adding that to the edge list. Entry for the forward list has the value present in the values array, but in the reverse edge will have the reciprocal value of that value. Okay, so we repeat this for all the equations in the input. Okay, so once the edge list and the adjacency list are built, then we enter this for loop. This will go over all the equations given in the queries array. Okay, so basically we initialize the start vertex with the first element in the each query, and the end vertex is initialized with the second element in the query. Okay, so each iteration we have to initialize the visited map with empty, because each equation, when we compute the value for the each query, we have to make a fresh graph traversal. So for that reason we have to initialize the visited map, and then we initialize the query val to 1.0. Okay, then we make a call to the DFS function, which takes the start vertex, end vertex, adjacency list, edge list, visited map, and the query value, which is 1. And when it returns, we assign the return value, and then we add that to the ret variable, and then we add that ret variable to the result. We repeat this for each query in the queries list, and finally we return the result. Next, let's take a look at the flowchart for the depth first traversal. Okay, so input for this procedure is the start and end vertex, and then the adjacency list map, edge list map, visited map, and the query value. Okay, so first we initialize the return value and the reached variable. The return value is initialized with -1 and the reached is initialized with false. Okay, so first thing we check is whether the start vertex and the end vertex are same. Okay, if that is true, we check whether the start vertex is present in the adjacency list. If they are present, we have to return the value 1.0, and we set the value of the reached to true. Otherwise we have to return the value -1 as the result for that query. Okay, and if the start and end vertex are not equal, then we have to mark the start vertex as visited, and then we have to get the neighbors list for that start vertex. Okay, and we go over the neighbors, check whether it is already visited. If it is visited, then go ahead and process the next neighbor. Otherwise, mark that neighbor as visited, and then we have to initialize the edge variable and its weight. Okay, so first we initialize the current edge as the start vertex plus dash plus the current neighbor we are processing. Okay, and then we look up that edge in the edge list and get the weight for that edge. Okay, and next we check whether that current neighbor is equal to the end vertex. If this is true, that means we reach the end vertex. So we simply return the current query value times the weight as the return value and reached boolean as true. Okay, otherwise we have to make a recursive call with the current neighbor as the start node, and then the query value will be updated by multiplying with the current edge's weight. Once this recursive call returns, we have to assign the return value in the reached variable and the retval variable. Next we check whether the reached is equal to true. That means in the recursive call we have seen the last vertex. So we have to return the current return value as the value of the expression. Otherwise, we repeat this recursively until we either reach the end vertex or we processed all the vertex in the graph. Then finally we return the reached boolean and the retval as the output. Let's move on to coding. First I initialize the adjacency list map with empty map of string to slice of string. Next I am initializing the edge list, which is of type map of string to float 64. This contains all the edges and its weight. Next I write the for loop to process all the equations in the equations array and populate the adjacency list and the edge list. So each iteration I extract the start vertex from each equation at index 0 and end vertex in each equation at index 1. Then I check whether there is an entry in the adjacency list for the start vertex. If it doesn't exist, then I initialize that with the empty slice of string. Next I add the end vertex as the neighbor of the start vertex, so I add that to that list. Next I do the similar thing for the end vertex. If there is no entry for the end vertex, then I initialize that with the empty slice of string and then append the start node as the neighbor of this end vertex. Next I build the edge list. First I construct the forward edge, concatenating the start vertex and the dash and then the end vertex. Then I add an entry for this edge in the edge list with the weight, basically the value of that equation. Next I do the same thing for the reverse edge. I reverse the vertices and add an entry for the reverse edge with value that is a reciprocal of the actual weight of the previous forward edge. Next I initialize the result with empty slice of float 64. Next I write the for loop to process all the queries. For each query I extract the start vertices at index 0 in that query and end vertex at index 1 in that query. Next I initialize the visited map with empty map of string to boolean. Next I initialize the query value with value 1. Next I make a call to the DFS function. This takes the start vertex, end vertex, adjacency list and edge list and visited map. The query value. Next I append the return value R to the result and finally I return the result. So I am going to write the DFS function. First I check whether the start node and end node are same. If that is the case, I check whether there is an entry for the start node in the adjacency list. If there is one, then I return 1 as the return value. Otherwise, I return -1 as the return value because the start node is not part of the graph. Next I mark the start node as visited and then I get the neighbors of the start node. Next I write a for loop to process all the neighbors. Each iteration I check whether the neighbor is already visited or not. If it is not visited, then I mark that node as visited. Next I construct the edge that connects the neighbor and the current node and the neighbor. Basically I concatenate start, dash and the neighbor. then I get the weight for that edge from the edge list. If the neighbor is equal to the end vertex, then I return true and the product of the current query value and the weight. Otherwise, I make a recursive call to the DFS function again with the current neighbor as the start node, and then I pass the product of the current query value and the weight as the query value for the recursive call. Next, I check the return value of the reached boolean. If it is true, that means we have reached the end vertex, so I return from here. Instead of processing the next neighbor, I return the return value of the DFS function. So if the end vertex is not reached, then finally we reach here, so I return false and -1. Next I'm going to run the test cases. All the tests passed. Next I'm going to submit this program. Cool, this program is accepted. Next I'm going to do the code walkthrough with sample input. The input equation has 3 equations: A divided by B, B divided by C, C divided by D, and the values for those equations are in the values array. And we are also given a 2 queries. One is x divided by y and the second one is a divided by c. The expected output is -1 and 6.0. We can model this input as a graph. So first we initialize the adjacent list and edge list to empty map. Then we build the adjacency list and the edge list, okay, by traversing the equations array. So after building the adjacency list, we have the adjacency list map, which has the list of neighbors for A is B, okay, and the list of neighbors for B is A and C, and the list of neighbors for C is B and D, and the list of neighbors for D is only C, okay. And in the edge list, for each direction we have an entry and its weight. So A to B has 2 and B to A has 0.5, okay. Likewise, for all the edges forward and reverse directions, we have an entry in the edge list, okay. Next we initialize the result array to an empty slice of float 64, and then we traverse the queries array. So in the iteration 0, we process the first query in the queries list, which is x comma y, okay. We initialize the visited map to empty and the query value to 1.0, and then we make a call to a DFS function with basically the first entry in the query is the start vertex and the second element in the list is an end vertex, okay. Basically we have to see whether there is a path from this vertex to this vertex, okay. So that's why we are performing the DFS, okay. So here first we check whether the start and end are equal, okay. In this case it is not equal. Next we mark that current node as visited, so the x is marked as visited. Then we try to get the neighbors list of x, okay. So in this case there is no entry for the vertex x in the adjacency list, so we have the neighbors list empty, okay. So this entire for loop will not be executed, okay. Then finally we return reached as false as the value for the reached variable and the result is -1. So once we return back from the DFS function, we append the R to the result array. So we have a -1 here. So that gets added to the result array. So at the end of the iteration 0 in this loop, we computed the value of the first query. So in the iteration 1, we processed the query a comma c. So the start vertex is a and the end vertex is c. Okay. So first we initialize the visited map to empty map and then initialize the query value to 1.0. Next we make a DFS function call with the start vertex, end vertex and the adjacency map and everything and the query value. Okay. So in the DFS function, first we check whether the start is equal to end. In this case it is not. So we go ahead and mark the start node as visited. So the node A is marked as visited. Okay. Then we get the neighbors list for A. So in this case then B is the only neighbor of A. So the neighbors list has B. Okay. Then we traverse the neighbors list and check whether that neighbor is not visited already. So in this case B is the only neighbor. So we check whether the B is visited or not. B is not yet visited, so we mark that as visited. And then we construct the edge that connects the current start node and this neighbor. Okay. So the current start node is A and this neighbor is B. So A dash B is the current edge. And then we fetch the value for that edge from the edge list. So in this case that A to B has value 2.0. So we get the weight as 2.0. Okay. Then we check whether the neighbor is equal to end. In this case it is not. B is not equal to C. So we go ahead and make another DFS call with the current neighbor as the start node. Okay. So the B is the start node in this recursive call. And then we pass the query value by multiplying the current edge's weight with the current query value. Okay. So the current query value is 1 and the weight is 2.0. So the query value become 2.0. Okay. So that value gets passed to the second DFS call. So when we enter here in this function, B is the start node. First thing we check whether the start node is equal to end. In this case it is not. So we go ahead and mark the current node as visited. B is marked as visited and then we get the neighbors of B. So in this case we get A comma C because A and C are neighbors of B. We traverse the neighbors in this for loop. We check whether A is visited already. In this case it is already visited, so we skip that node. Okay. And in the iteration 1 we have the neighbor C. Okay. So we check whether that C is visited already or not. In this case it is not yet visited, so we mark that node as visited. Okay. Then we form the edge which is connecting the current node and the current neighbor. So current node is B and the current neighbor is C. So the current edge is B to C and its weight is 3.0. The weight is set with 3.0. Next we check whether current neighbor is equal to end. Current neighbor C is equal to the end C. So in this case we return the reached value as true and we return the query value times weight as the result. Okay. So in this case the current weight is 3.0 and the query value is 2.0. So 2.0 2 times 3 we set retval as 6.0. That value will be returned from this function. So the DFS function returns the 6.0 as the result value, and when the first level function receives the result reached as true, then without processing further neighbors we return from here. So eventually we return back to the calculate equation function. We come back here. So here we add that 6.0 to the result. So the 6.0 is appended to the result. We reach the end of the query, so we finally return the result -1, 6.0. That is an expected output. Next, I'm going to do the time and space complexity analysis for this solution. Time complexity for this solution is order of m times n, where m is the number of queries in the input and n is the total number of variables in the equations. Okay, let's take a look at the case 1, where the equations has 3 equation and there are 4 unique variables present in this equations. Total number of variables is 4 and the number of queries is 2. We need to process m number of queries. Okay, so for each query we have to make a DFS call, which in the worst case it traverses all the elements in the graph. If there are n vertices in the graph, then we process m times n number of nodes as we traverse the graph. For this input, basically there are 2 times 4, 8 nodes are processed in order to compute the result. Okay, so if there are m queries in the input and n unique variables in the equations, then the solution process m times n number of vertices in the graph. Okay, so that's why the time complexity is order of m times n. Space complexity is order of n because we need to allocate space for the visited status and then the adjacency list and the edge list. For that, we need to allocate space for all the variables in the equations. So if there are n number of unique variables in the equations, then we need to allocate space for those n elements. So that's why the space complexity is order of n. Thanks for watching this video. Have a great day.